So the topic of today's lecture is curve fitting. Okay, so one way of thinking about machine learning is basically fitting some sort of function to data. And so today I want to just kind of talk about the basic idea of how that process works. Before we start talking about really complicated models, let's just talk about fitting a line or a polynomial to a bunch of data points, just as a refresher. And again, this is a good kind of point for you to evaluate if you understand the calculus and the linear algebra that I'm talking about in today's lecture. That's kind of like the right level for this class. Okay, so I think I mentioned this earlier, is that the problem of what's called regression is basically fitting a continuous valued output to input data. Okay, and so a good starting point for this, like I said, is called curve fitting. Okay, so the idea is that we have input, which we're going to call x, and these are real valued numbers. Initially, we're just going to talk about x as like one dimension, but we'll generalize this to x being a vector. And the output, let's call t, is also real valued. And so what we have to kind of solve this problem is first we have training data, right? So the training data takes the form of a bunch of pairs of x and y. So we have like x1, t1, ... all the way to xn, tn. You can imagine these like a whole bunch of just like xy points in the plane, okay? And our goal is to be able to make a good prediction of t given some new input x, okay? So the goal is predict, t hat given a new input x hat. And so we mentioned this earlier, that the goal of this training process is to design something that kind of generalizes from the data, right? So it's not hard to make a function, as we'll see, that basically exactly duplicates the input-output process. I mean, one very obvious thing to do is to make just like a if statement, thing. It's like if the input is x1, output t1, right? That would do a great job on the input data, but it wouldn't generalize at all because it wouldn't know what to do with unseen data, right? So we want to be able to design functions that generalize, okay? And so one key kind of hypothesis is that the outputs are related to the inputs by some sort of unknown but regular function, okay? So basically, and let me just write down the word generalize because I want to make sure that's in your notes somewhere. Right, so this kind of idea of predicting some new output from a new input is called generalization, okay? And so a key idea is that the outputs and inputs are related by some function, right? So kind of the, what's the right word? The idea is that the observations or outputs t are related to x by some unknown function, right? For example, like the t ideal is just some nice function of x. If we could estimate f, or the parameters of f, then we could do a 100% job of prediction, right? But the tricky part is that we are going to assume that things are corrupted by noise, right? And we'll be a little more precise about what that means. But basically, the idea is that no observation is perfect, right? There are always kind of confounding factors that make it impossible for us to exactly predict the output from the input, right? So for example, if I'm a photographer, right? So say I want to model the picture I take at the scene given the 3D environment, right? One thing that I'm always dealing with in things like low light is image sensor noise, right? So I'm in a dark room, I take a picture of a flat wall. Ideally, that wall should be like a smooth gradient, but in practice, it looks kind of speckly. And the speckly is due to the fact that not enough light is reaching my sensor. There may be some, other things going on in the room, like rays of light hitting little dust mites and bouncing off and coming back. So I don't get this idealized picture. I get picture plus noise, right? And the same is true in so many signal processing applications, right? Or just real world observations, right? You can imagine that, yes, maybe there is some sort of like grand model that predicts Wall Street prices from a bunch of inputs, but there's so much variability in terms of like, did this investor, have a full breakfast this morning or not, right? Things that you can't model in your system that end up resulting in noise in your observations, right? So kind of the idea is that in 1D, we have this idea that on the x-axis, we have a bunch of points, and maybe our kind of underlying model looks like something really smooth and regular. This is kind of like the underlying model. But in practice, what we see are a bunch of xy coordinates that are more like this, right? Sometimes I'm below the curve, sometimes I'm like way above the curve, right? So this is x, this is t. And so this is kind of, in some sense, I guess it's unsure. I'll draw in red for the next one. This is like the ideal answer, but what we see is not ideal, right? So the actual observations are noisy. Okay, so far so good, right? Questions or comments? Okay, so what would be a good model for fitting the data, right? So one thing that you learn about in calculus, for example, is the Taylor series, right? The Taylor series, basically the idea is I can take any function and I can approximate it by a polynomial. I may need lots and lots of terms to get all the way out to a good approximation, but that's exactly what a function approximation is. Another function approximation, if you're an ECSE major, you learned about is the Fourier series, the Fourier transform, right? I can take any function, I can model it like the sum of a bunch of sine and cosines offset by phase, right? So those are both different ways of building a model for the data that we have, okay? And so let's just start with the polynomial case, right? So what's a good model? Well, the easiest thing is, like I said, a polynomial. So I have a function that looks like this. I take the input value x, and then what I have is a constant term plus something times x plus something times x squared plus dot 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 something times x to the m. Okay, and so this m here is what we would call kind of like the order of the polynomial. And then these, values here are what we want to learn, right? These are called weights. I mean, you could call them coefficients, but, kind of in a machine learning frame of mind, we want to call them weights, okay? And so let's think about what we know. So if m equals 0, that means that actually I don't have any of this part, and all I have is w0. That means that I basically have a constant, right? If m equals 1, what I have is this part, which is basically a slope-intercept thing. So this is just a straight line. And so on. Like m equals 2 is a quadratic function, etc. And so the goal is to tune the values of these w's, the coefficients or the weights, to make the fit of the data the best that we can, right? So now what we need is kind of like a measurement that says, how well does my model y match my data t, okay? And so we need to kind of find the best weights is some sort of a function that says, how good are these weights? The natural thing to do is to look at the differences and square them up, right? So we need an error function. Sometimes you see this called a cost function or a loss function. We'll use those terms as we go on in the class. That, basically quantifies how good the fit is. Okay. And so what's a natural error function, right? So I have an error function. It's a function of the weights. This now W is basically like a vector of all of the weights, right? W0 through Wm. For an mth order polynomial, I have m plus 1 numbers I need to estimate, okay? And so this error function, the natural thing is to say, okay, I'm going to add up over all the data points I have what I saw versus what I predict, right? So I'm going to sum up from n equals 1 to capital N. Remember, capital N is the number of points that I have. This, again, reminder, is the number of data points. And then I'm going to take what I saw minus what I predict. And I'm going to square it because I care about basically, I don't care about positive or negative errors. I care about kind of like, absolute error in some sense. And generally, as you'll see, it's much easier to deal with things when we square them. It is to take a look at absolute values and so on. In a way, if you're a math person, it's like the L2 error of the observations, right? So again, just to remind you, this is the kind of observation, and this is the model. And just as a kind of mathematical convenience, you'll see why we do this later, I'm just going to put a 1/2 in front of here, right? The 1/2 doesn't really make any difference to the numbers that we find. It's just a scaling of the overall cost function, right? Now, if the model fit the data exactly, my number would be 0, right? And so, of course, you never quite get there, but that's what you hope for, right? And let's just be explicit about what this is. This is like saying, OK, I'm going to take the sum of the observation minus the model, Wm, Xm, and I'm going to square this whole thing. OK. So now how are we actually going to solve this problem, right? Well, this is where your calculus comes in, right? We're going to take the derivative of this function. Since we have a vector of things we have to tune, we're actually going to take the gradient of this function, and we're going to set that equal to 0, OK? So this is where it's helpful to, instead of thinking about things like element by element, it's helpful to think about this as a linear algebra problem. And so this is why anyone who is serious about machine learning really should take a full-on linear algebra class. I mean, if we required linear algebra, math 4100 or whatever it is here at RPI, that would probably have the number of people, because I don't think everyone in this room has taken linear algebra. But if you are serious about going on into this world, I do really recommend that you take a real linear algebra course, not just the one that you get at the end of third semester calculus. Okay, so let's rewrite this as kind of a matrix vector thing, right? So, kind of linear algebra style. The error function is 1/2. So the sum of square root of a vector is also known as the norm of a vector. So let me just write some notation here, and then we'll talk about what this means, right? So I have these double bars. Then I have basically my observations. And I have my unknowns. So how do I map this function here onto this linear algebra problem, right? So basically the first row is like saying t1 minus this function of x1, right? So here, what has to go here is basically saying I multiply w0 by 1, I multiply w1 by x1, w2 by x2, dot, dot, dot. Oh, I'm sorry, not that, x1 squared is what I want, x1 to the m. Right? So this first row is like saying, what is the model fit for data point number 1, right? So here I have all the powers of x1. Then the next row looks like 1, x2, x2 squared, x2 to the m, all the way down to 1, xn, xn squared, xn to the m, right? So hopefully that makes some sense. So this is a n by 1 vector. This is an it's like an n plus 1 by 1 vector. And then this is an n by m plus 1 matrix, right? N rows and an n plus 1 columns. Okay, so hopefully this kind of motion into linear algebra space is not too unfamiliar. And now I'm going to kind of replace this by writing this like vectors, right? Vectors and matrices. So here, I'm just going to call this, something that looks like b minus aw squared, right? So again, this guy here, just to remind you, this is called the, 2 norm. And to be really explicit, I'll put this 2 down here, of a vector. This is basically like the Euclidean length of a vector. That's what those double bars with the 2 mean. And so this is like saying, OK, what I want to do is I have a vector B, and I have a matrix A, and I want to find AW that is close as possible to B, right? So again, one thing to kind of think about here is like if you took linear algebra, you're trying to basically find something that is in the column space of A that is as close as possible to B, right? We'll talk about the geometry of this in another lecture, OK? But now what I want to do is think about, OK, so this is basically another way of writing this is like saying, B minus AW transpose B minus AW, right? So here, what is this? This is like saying I have a n by 1 vector here. That's the kind of raw errors. And I have a 1 by n vector here. And so this whole thing is a scalar value. It's just a number that says how well did I do overall. OK? And so again, this is, I think, good linear algebra review, right? Forming up this matrix vector equation. That's the kind of thing that I could easily ask you to do on a homework or on an exam to say, OK, here's some data points. Tell me about what this matrix vector equation looks like, right? And so let's think about, when can I solve this equation and when can I not, right? So for example, say that I have fewer observations than parameters, right? So say I only gave you 3 data points, and I'm trying to fit, or maybe like make it super simple. I give you 1 data point, and I'm asking you to fit a straight line through it, right? Well, there are an infinite number of straight lines that can go through that point, right? I need to have at least 2 points to nail down the line. And the same way, if I have fewer data points than I have parameters, then that means there are basically an infinite number of ways to exactly satisfy those constraints, right? So that kind of comes down to whether this matrix here is square or not, right? So let's just remember that if n is less than m plus 1, that's what's called under-constrained. There are basically infinitely many solutions in general, and we need to find a way to pick a good one, right? And we'll talk about what that means in a minute, picking a good one of these infinite number of solutions, right? If n is exactly equal to m plus 1, that means this matrix is square, and I should be able to solve this problem exactly in general. It is possible that there are like dependent rows and stuff like that, but in the general case, when I have exactly as many parameters as I have data points, then I can solve the problem with 0 error. That means that the curve will go exactly through those points. So usually that means that there is a exact solution. 1. And if I have more data than I have parameters, that means that it's really not possible to satisfy all these equations at the same time, right? So if I gave you, 3 points in general and asked you to fit a line to them, well, there's no guarantee that those 3 points are going to be on a straight line, right? You're going to have to just find the best line, and we'll talk about what best means in a second, to go through those points, right? So if n is greater than m plus 1, then this is basically what's called over-constrained. And basically, there's usually no exact solution, but we want to minimize this function error, right? So this is like saying that here I can definitely get e equals 0 in this case and e equals 0 in this case, but I can't get e equals 0 in this case. And so this is usually the situation we find ourselves in. Well, I guess I should take it back. So in machine learning, you find both of these situations, right? So a lot of times you have, more data sets, more data than you have parameters, in which case you're in this kind of like last situation, this least squares problem of doing the best that you can to fit the data, right? But then, these days, there are these machine learning algorithms that are like billions of parameters. Even though it's also using like a huge amount of training data, it may be that you have more parameters than you have data points, in which case you're kind of in the top situation, and you have to find a way to choose from one of these good situations, right? So we're going to talk about all these kind of situations in class, okay? So this problem is kind of what I want to say in general, is that overall what we want to do, or let me stop and ask. Any questions or comments about what I said so far? This is good linear algebra review, right? And so what we want to do is, we want in general to minimize this error function or this cost function E of W. Okay. If we're lucky, we get 0. If we're not lucky, we get some number, but we want that number to be as small as possible. That means we fit the data as well as possible. And so again, kind of graphically, just to look at this picture, what that means is that we are trying to minimize the sum of square distances between my observations and whatever my model comes up with, right? We're trying to make those distances as small as possible. Okay, so how do we actually do this? Well, again, this is calculus, right? Take the gradient and set it equal to 0, right? So just like any other function. So from calculus, we have to take the gradient of E and set it equal to 0, right? That place is going to be where we get our minimizer. So this W is the minimizer. And remember, this E of W is a single number, right? So I should be able to take the gradient of that number with respect to my vector, right? So if I write this out in a little more detail, let me multiply this out. I got 1/2 times B transpose B minus, let's see here, W transpose B minus B transpose AW plus W transpose A W. So again, if you don't know how I expanded this into these things, that's another good linear algebra refresher course. All I'm doing is I'm taking these 4 terms and making sure that when I transpose something, I've got the transpose in the right direction and so on, right? So this is, again, pretty straightforward. Now I want to, and this is a scalar, right, meaning a single number. Now I want to take the gradient, right? The gradient is a vector, because I have all these parameters. So it's going to be a vector. Well, what is this vector? Well, this guy is constant, right? Because I only have to look at things that depend on W, right? So this thing is a constant. Then the derivative of this guy is 1/2 A transpose B. The derivative of this guy is 1/2 A transpose B. The derivative of this guy is 1/2 A transpose AW. And so actually, I take it back. This is just this because I have the 1/2 there. So this is equal to minus A transpose B plus A transpose AW. So this is the point where you may be like, where did this come from, right? So this is a good thing. If you don't see where this is coming from, you can always get there by kind of working it out element by element to kind of convince you that this is why it works, right? In general, it's like saying the derivative of something times a vector, right? So let me just kind of do a quick thing here. This is like saying that the gradient of W of like A transpose W is this vector A. The gradient with respect to W of basically W transpose some matrix W is equal to AW, right? That's just kind of a reminder of where this came from, right? So here, basically I've got this vector A transpose B that is playing the role of basically multiplying by W. That's where this A transpose B come from. This here is just a number, right? So if I transpose this, I get the same thing as this. That's why I get the same thing again. And then this here, the A transpose A, is playing the role of this thing in the middle, right? So again, you can kind of convince yourself just by looking at this element by element that, yeah, this is why it's true. if we are talking about an exam where I'm asking you to take derivatives, this is a good thing to put in your crib sheet, perhaps, if you don't remember how these things work, right? And so now, this is a vector, right? This is a vector. And so to set this equal to 0, the kind of key equation is the following. A transpose A W equals A transpose B. I move that over onto the right-hand side. And now, how do I solve this problem? Well, I take the inverse of this matrix, and my optimal answer is this. So here, this matrix is, if I go back to what I defined these things as, right? So this matrix here is A transpose is an m plus 1 by n matrix. This is like an m plus 1 by m plus 1 matrix. So here, this is like m plus 1 by m plus 1. And then this thing here is an n by 1 vector. This thing here is an m plus 1 by n matrix. So all the numbers basically work out. And what I get over here is an m plus 1 by 1 vector, right? And those are the optimal weights, because I have basically the constant part plus these m coefficients on the powers of x. And so for those of you that know a little bit of linear algebra, this hopefully is a familiar equation, right? This is basically the least squares solution. And in particular, this thing here has a special name. Sometimes you see like A with a little bit of a cross like that. This is called the pseudo-inverse. Right? So A itself, in general, is a rectangular matrix. So I can't take the inverse of anything but a square matrix, right? So here, this is kind of like playing the role of A inverse. And in fact, when A is square, the pseudo-inverse and the inverse are the same thing, right? But in general, they're not. So I need to basically find a way to make a pseudo-inverse matrix, right? So again, this is good practice for, do I remember linear algebra, right? So again, this is a good thing to kind of like, review matrix vectors and so on, right? And so now we should be able to solve our problem, right? So this is basically the way that I solve the least squares problem for fitting a polynomial to data, okay? And that's actually, problem 1 on the homework is, doing that, right? So I'm not going to write the code in front of you because obviously I want you to write the code yourself. But let's take a look. So let me switch over to browser. So here, what I'm doing, and hopefully I'm still running the kernel here. Here what I'm doing is I'm running Matlab inside this Jupyter notebook. Anyone who knows Python is like, why is he doing it this way? Well, that's just the way I'm doing it, right? So let's make sure I'm online here. All right, so I have Matlab. OK, so let's make some data and solve some problems, right? So let's suppose that I just look at some linearly spaced points between 0 and 1. This is like saying, give me 10 evenly spaced points between 0 and 1, right? So I have 10 points, so I can fit no more than a 9th degree polynomial, exactly, right? And so now what I'm going to do is I'm going to say, let's make up some data that is kind of like a function. So here I'm going to make basically a sine wave, 2 pi x, and I'm going to add some noise to it, right? Just like some random noise, the size of x, right? And now I'm going to plot x and y. Well, actually, yeah, let me plot x and y. So here, what I'm going to do is I'm going to plot, I guess you can't see what I'm doing here. I'm going to plot also, like I'm going to call y true be the actual kind of underlying model. and I'm going to plot x, y true in green. Right, so what I see is something like this. The red dots are my actual data. I'm going to make this a little bit smaller here. So the red dots are my actual data. The green points are what the curve actually looks like. And so you can see that, you know, some of these red points are right on the button and some of them are quite far off, right? Because if you think about it, I added, you know, some Gaussian noise, right, that had zero mean and unit variance, which I generally expect to be kind of like, you know, not too far away from the curve, but there's some points like this one over here definitely is, you know, a real outlier, right? So that may cause us some problems when we're fitting our data. So now what I did is I wrote a function, and let me just figure out for 1 second how to make this better, because I feel like I want you to be able to see what I'm doing. So let me make this a little bit bigger. This is an OBS problem, so apologize for this for a second here. So what I'm going to do is I'm going to resize this. All right, a little bit better. I know that now this is too hard to see, so let me go back to here. Okay. Okay, so now what I want to do is fit this set of red points to some data, okay? Or to a function. And so my function, I wrote a function called, what did I call it? I called it 1D fit. Now let me just say that yes, there are built-in Matlab functions that can do this for you. The whole point of this class is for you to understand what's under the hood of these functions. This is literally just like 2 lines of Matlab code, right? So when you're writing the homework, don't like immediately just Google on Stack Overflow, how do I fit points of data in Matlab, right? I want you to actually take the equations I just wrote down and figure out what this linear system is and solve it, right? And so here, let me just say, what did I call this data again? 1D fit. So if I say, you know, 1D fit x, y, 0, that's like saying fit me a 0th degree polynomial. And a 0th degree polynomial is just a line, right? So this is the best constant that goes through these points, right? You can see it's got, you know, a non-zero error. It's not a very good fit to the data, right? So if I then say, okay, give me the best straight line fit to the data, I get a fit that looks like this, right? Looks pretty good. Error went down. And then as I increase the number of you know, polynomial coefficients, I can do better and better, right? Let's try 4. Right? So now I get something that's kind of, you know, doing a better job of fitting through the data. And I can kind of take this to the limit, right? So if I take this to the limit of like, you know, 9, I get a function that indeed goes through all the data points exactly, right? My error is, you know, basically 0. So, you know, that's great for, you know, curve fitting, but bad for generalization, right? Because clearly, I know from my picture up here, if I were to superimpose the true thing onto here, you know, this is really not a very good fit of the data at all in terms of what the underlying model is, right? The problem, of course, is the noise. The noise is throwing our estimate off. So this is what's called overfitting, okay? So that's, again, a critical thing to know, and I'm going to write this down on my notes for a second here. So, you know, just in general, to kind of write down what we saw, right? So if I kind of do this on my paper and pencil, so kind of what we saw was something like this. So maybe what we get is a line like this for m equals 0, a line like this for m equals 1, you know, something that's not bad. I'm sorry I don't have more colored pens for m equals 3. But the big thing that we may have is something like this, right? So when I have, you know, too many parameters, what I may see is something like this. And this is called overfitting. Right? This is going to be really crappy at generalizing to any new unseen data, right? So the problem of choosing the right value of m is what's called model selection, right? How do I know which of these models is the best for my data? Clearly, just looking at the fit alone is not really the right answer, because the error is getting lower and lower, right? So the more parameters I use, I can certainly do better and better in fitting the data. So I can't just look at that error alone. I have to think about some other considerations also, right? So this then is what kind of comes back to this idea of a training set versus a testing set, which we talked about last time, right? So before I go on, let me ask questions or comments about what we've seen so far. And I'm going to ask you to basically duplicate this very thing on your first problem of your homework, right? So, choosing the right M is called model selection. And, more parameters always, in theory, can lead to better fits. So we need more than just the error function itself on the training data, right? So this is where then we kind of talk about a testing set, right? So we can tell how well a model generalizes by, evaluating on a testing set, right? So what I do is I split my training data up into some part that I'm going to use to tune my model parameters with, and then some part that I'm going to evaluate on. And this is kind of where the true proof of how well the model generalizes is, right? Because yes, I could do, hopefully really well on the training data. The question is, how well does it work on the testing data, okay? And so that's the crux of it, right? And so since these two data sets may have different amounts of data, right? So typically, well, I guess I shouldn't say typically. I think that usually what happens is that you have more training data than you do testing data, at least in my computer vision problems, right? So kind of what happens is that I have to have a fair basis for comparison, right? Because certainly if I have, 10,000 data points here and 1,000 data points in the testing data set, then I can't just compare, this error and this error because this has 10 times as many measurements, right? So I should just generally expect to do 10 times as worse. Kind of what I want to do is scale the error that I measure according to how much data I have, right? So a good, so since training and testing data generally have different sizes, for a fair comparison, we can measure what's called the RMS error, root mean square. It stands for root mean square, right? That's basically saying I evaluate, my error function on a given data set kind of by dividing by n. Since this has a squared in the definition of the function, I take the square root, and this 2 is just to kind of compensate for that 1/2 that we had in the error function, right? And so kind of typically what you see is that if I plot the kind of like, in our case, the number of parameters against the RMS error of the best model I can get with those parameters, kind of what I expect to see is that the training data just gets better and better, right? So training data probably, kind of starts off, and kind of comes down, and it may even get down to 0, right? So the training data can only get better. Usually what happens is that the testing data is, first of all, generally worse than the training data because I didn't see any of that while I was tuning my parameters, right? So the testing data probably is always going to be higher, but what we kind of hope to see is that maybe it goes kind of like down like this And then it gets kind of worse, right? Because this is like saying that as I overfit to the training data, then it's going to be worse on the testing data, right? So this is like saying my testing data generally has this kind of like elbow-like behavior where, you know, I can have overfitting at, you know, the right end. And so what I might do is say, okay, I'm going to look at this thing, and I'm going to choose this to be my m that I use for my model going forward, right? So I have a choice of m from, you know, straight line to 10th degree polynomial, and maybe I find that if I look at the testing data, the 4th order polynomial is the best one. Right? Okay, so let me ask questions or comments so far. Okay, so let's look at the actual values that we got for these w's, right? So if I go back to my, my browser here, so let's look at, again, the you know, straight line fit to the data. I guess I have to take my semicolon off of here. So here what I'm doing is I'm outputting the weights. This thing at the bottom basically says my constant value is 0.25 and my linear slope is minus 1.4. Again, I should be able to read that off from this picture because I've got a negative slope, right? Yeah, fine, whatever. Let's suppose I did this with, like, you know, 4. Well, now these numbers are a little bit bigger, right? The 4th degree number is like 43, and the 3rd degree number is like minus 78, and the constant number is still on the order of 1, right? And then let's say I, you know, go back to my great fit, right, with 9. Goes through all the points, but the actual values of these weights at the high end are huge, right? If you can't read it, basically this is like 10 to the 6th times these numbers, right? So that means that the, you know, 7th, 8th, 9th, you know, order terms are all like massive numbers compared to the constant term and the linear term, right? One way of thinking about this is that the, you know, the polynomial coefficients have to work really hard to go exactly through those points, which means I've got a really weird polynomial. And you can imagine that if I got a different realization of random noise, that these numbers would be totally different, right? So like, you know, I guess we could do that experiment here. So let's remember, you know, these numbers, wold equals ants. Okay. So here's my old values. And then let's just go back and redo this experiment with the same values of x and a new realization of data, right? So now, I guess that's all I did, right? Just make sure I did this right. So here, new realization of data, new fit, and let's compare these two things, right? I must not have actually executed this. All right, so now this curve definitely looks different. My values are different, and if I compare the old coefficients and the new coefficients, I can see that they really don't match up very well at all, especially on the high end, right? Again, these numbers are all huge at the high end. So, you know, I've just changed the noise, you know, random noise that was added to it, and I got a completely different fitting function, right? Which is a little bit disconcerting, right? I would like there not to be that level of kind of like, you know, sensitivity to the random noise. In some sense, what's happening is that you're overfitting to the noise, right? So let's just say, let me write that on the paper here. So the danger is that we're overfitting to the random noise in the observations, which is to say that the parameters for high values of m are very sensitive. So again, this kind of has to do in a way with trading off the amount of data you have with the number of parameters that you're fitting, right? So let's kind of turn this problem around a little bit, and instead of using 10 data points, let's just fit like 100 data points, right? So if I go back to here and I say, okay, let's go back here, and instead of creating 10 data points, I'm going to make 100 data points. And I don't want to see them on the screen. And now I'm going to make my y, and I'm going to plot my points. So here, this is now kind of like the true fit plus the noise, and I've got lots more data points now. And now if I say, okay, I'm going to fit, say, a fourth degree polynomial to those points, well, actually I did pretty well, right? Because I'm not so sensitive to the noise. And if I were to, just use a different realization of noise, right? So go back here and make some new points and then fit the data again, hopefully, my blue curve still looks pretty much like it should, right? So this is kind of an illustration of saying that kind of rule of thumb is that you want to have more data points substantially than you do parameters to fit to be sure that you're not so sensitive to the noise, right? So in general, there is no great rule of thumb. Sometimes it's like, okay, you should have at least like 5 times as many data points as you do parameters. But I mean, it totally depends on things. And of course, this doesn't totally apply to some of the more complicated models we're going to talk about later in the semester. But certainly for just like curve fitting in general, which is just all we're talking about today, that's probably a good rule of thumb, is that you don't want to have, so close to the number of parameters as data points that you have, right? So obviously, in general, you want to have as much data as you can. Question?
Why is it again that you want to have similar number of parameters as data points?
I want more, for this problem, I want to have more data points than parameters, right? So here I've got 100 data points, and I've only got 4 parameters, and so each of these individual contributions of random noise is not moving my solution around too much, right? Because it's only like 1/100th of the cost function, right? So if I change any of those data points a little bit, it doesn't change too much, right? And we'll talk about at the end a little bit more of a probability interpretation of why things get better with more data points too. Other questions or comments? So this is also a good point to introduce another way of preventing the curve from like wildly oscillating between points and having some sort of crazy parameters at the high end of the x to the m, right? So another thing we can do to prevent that is a key idea called regularization. So, another way, to combat overfitting is what's called regularization. And we'll come across this idea in many different ways as we kind of go forward in class, right? So the idea is to define a slightly different version of the cost function. I'm just going to put a little hat on it, E tilde, right? Here, this is the same part that we had before. I sum up all my squared errors, right? And then what I'm going to do is I'm going to add this guy here. This is basically like saying I'm going to add, I'm not adding this twice, I'm just kind of like expanding out what I mean by it. This is like saying I add W0 squared plus W1 squared all the way up to WM squared, right? This is like saying I now want to minimize this whole thing, right? Meaning that if the coefficients are really large, that is going to totally tank my error fitting score, right? So this is going to bias my solution to have smaller values of W, right? Because remember that the error of the first part we were seeing on these examples was on the order of like, 10 or 100 was my E function before. Now if I'm going to square all the W's and add up to it, well, now those numbers are going to be huge, right? They're going to dwarf the error function itself. That's why this function lambda is something that the user kind of tunes to say, well, how important is it to me to have small values of W versus having really good error fit, right? So here, this is kind of like a tunable parameter by the user that says kind of like, how much am I forcing these coefficients down to 0, right? So a big W, or a big lambda, sorry, this basically encourages W to be small. Conversely, if I just have lambda equals 0, then the function is exactly the same, and then the curve can do whatever it wants, right? It's not constrained at all. So you can think about lambda as kind of like a dial that I can kind of turn up to say, hey, don't go out of control on your parameters, right? OK. And so let's look at this in the example that we did before. So if I go back to, I'm worried about whether this will work on this example. What could go wrong? Trying an untrained example here. So let's say I have a four-dimensional cost function. This is actually not too bad. Maybe I should try going back to my example with 10 parameters, because I think that's a good illustration. OK. So again, if I fit like, an 8th degree polynomial to that data, it's going to be pretty wiggly, right? So the fit is going to be pretty good, but it's also going to be a little bit, unlike the underlying function. It's actually not too bad, because I think we got lucky on the way that these points got distributed, right? But now I have an extra function, or I have an extra number that I put in my function that's basically my lambda, right? So if I say lambda equals 0, I should get exactly the same fit, right? Because I haven't done anything. If I say lambda equals, say, 10, that's like saying I'm encouraging the W values to be really small. So that means that I'm getting a almost flat line that doesn't have any real, cubic or quadratic contribution, right? And if I, make it a little bit less, say 3. Actually, it seems like I need to make this a little bit less to make it do anything different than a line, say 0.5. So the more that I turn down lambda, the closer I get to going through all the points, right? And the lower my error gets. But also, I can kind of control, well, how smooth is my curve going to be by what this value of lambda is, right? And so that's kind of like the idea is that, we are trading off kind of like curve complexity with quality of fit, right? And, the error is going to always be worse if I turn lambda up, but the curve fit may look more like what we expect as humans, right? So when you're kind of in a limited data regime where you're in the position of having to choose between all these possible things that have pretty good fit, well, then maybe the bias should be that you should make your weights as small as they should be, right? So that's what we can use, is we kind of like modify our cost function to say, hey, I have a belief about what these weights should be. And again, if we want to be all probability about it, we could think about that also as kind of like a prior belief about what the weights should be, right? So we're kind of saying, my prior belief before I see any data is I want small weights, right? Now I actually see the data, and I have to trade off, fit with model, right? That's always the kind of trade-off that we have in machine learning in general, okay? And so now, in a way, we have two parameters that we can kind of choose to turn, right? We can choose the model complexity by itself, M, and we can choose lambda, which says how important do we think the model, how small do we want the model parameters to be, right? This is not saying that I have to like totally zero out the big terms. It's just saying that I want those terms to be small. And if I was really more, what's the right word? Picky, I could say that maybe what I want to do is I want to have a different lambda on every one of those W's, right? To say, well, it's OK for the W0 and W1 to be large, but I really don't want the big values of W to be that big. So maybe I have a decreasing schedule of lambda, like lambda 0, lambda 1, all the way to lambda m, and I can turn those numbers to be what I want. Usually it's easy just to put lambda as a multiplier, right? But that's kind of like the idea. So in a way, this kind of brings up this concept of what are called hyperparameters, right? So, now we can kind of tune both m and lambda to give us a fit that we're happy with. And so these, in this kind of terminology, one way to think about these are what are called hyperparameters, which means that I'm not training those in my model, right? I'm not tuning those like I'm tuning the weights. Instead, I'm kind of like doing an outer loop over the m and the lambda to kind of like get those knobs set the way I want them to look as good as possible, for example, on the testing data, right? So kind of the way that you'd use this in practice is I told you, okay, never train on the testing data, and that's true. So how would I address this problem? What I might do in practice is to say, okay, now I have, again, training and testing data. The testing data is still sacrosanct, right? Never use this in training. Then I have my testing data, and what I may do is I may draw a line here and say, this is for training, for tuning the model parameters, right? Like the weights. This is what's called validation to tune what's called the hyperparameters. So I may say, okay, I'm given some trained data. I'm going to save some of that trained data to kind of find the best m and lambda without cheating and looking at the testing data. And then I'm going to, basically for every possible value or every value I want to explore over here, I train the model with those hyperparameters. I see how well I did. And at the end of this process, I freeze everything I did, and I evaluate on the testing data, right? That's the way you should do it. So questions about that kind of concept? So oftentimes when we talk about a split of data, like if you download a data set from somewhere, you may see that data is split into training, validation, and testing. And that's what that means, is the idea is that you don't use the validation data in your W tuning, you use it in your hyperparameter tuning to be happy. And then you evaluate on the testing data. So there are lots of situations where you may not have a lot of testing data or a lot of training data in the first place. Maybe you can't afford to save 30% of your training data for this validation process. Then you can do some things that are called cross-validation. So if you don't have a lot of training data, you can, you may not have enough for, kind of like a holdout validation. So then what you can do is what's called cross-validation. The idea is that what I do is I take my training data and I kind of split it up into pieces, right? So it's kind of like saying, okay, for this experiment, I'm going to use this to train here, and then I'm going to validate on this piece. And then I'm going to do the same experiment, but I rearrange where I put the validation part. So basically, I could kind of split the data into what's called, 4 folds. So that's like saying, I basically have a number of chunks, a number of different ways of chunking up the data into training and validation, and I'm moving around where I put the validation part. And then I average my performance over the whole thing. So basically, we, average performance over all of the folds. And if life is really hard and you don't have like barely any trained data or barely any testing data, barely any trained data, you can imagine that I could kind of like have, okay, I'm going to use all but one of my points for training, and I'm going to use this final point for evaluation. I'm going to do that n times. That's called leave one out, right? So sometimes, like I've been in situations where I'm doing a problem with like medical image segmentation, and they gave me like 20 CAT scans of people, right? 20 is not really enough to be able to do much at all, right? So I had to do some sort of leave one out thing where I'd say, okay, I'm going to, design my model on 19 of these things, and I'm going to evaluate on the 20th, and I'm going to average the results on those 20 experiments to see where I got, right? That's kind of like the worst case scenario. Of course, many problems in machine learning these days have a huge amount of data, and so it's not so hard to find the validation part. But there are still many cases where like someone will come and say, oh, I want to apply machine learning to this environment that I have. Like, let's just do it. And I was like, okay, well, how much data do you have? It's like, well, we got like 100 measurements, right? That's not really enough to do. So you have to think about how am I going to do cross-validation in a way that's convincing, right? Okay, so questions or comments about that? Okay, so the last thing I want to talk about is kind of bringing two more things. One thing is kind of bringing a more probability perspective into this, okay? So now you were told that you needed to have probability for this class, so why do we want that, right? So one of the things is thinking about, okay, so if we all took probability, we should be able to kind of reason about, if I show you the data and I have a model for the noise, right? How was the data corrupted? I should be able to find the probabilistically best answer, right? If you remember from your probability class, there was something called the maximum likelihood estimate, right? We're going to talk about that again next time. So next time is going to be mostly about probability. This is like a little bit of an entree into probability, right? So kind of like the probability perspective is that, we imagine that, well, let's just remember, one thing that's really important from probability is the Gaussian distribution. And sometimes you see this, n mu sigma squared, right? This n stands for normal, right? Which is why sometimes you also hear this called the normal distribution. What is this formula? And then this is called a probability density function. We're going to talk about this again in detail next time. So this is kind of like, today was kind of like calculus linear algebra review. This is more like the beginnings of probability review. What this looks like is a kind of famous bell curve that is centered around mu, right? So often it's natural to make this assumption that the observations that I have are corrupted by noise that is zero mean Gaussian noise, right? So a typical assumption is that observations that you see are equal to some sort of underlying model that is true plus IID zero mean Gaussian noise, right? IID stands for identically and independently distributed. It means that the noise that I see at every point is basically coming from the same Gaussian model, and that noises at different data points have nothing to do with each other. They're all independent, right? If you had some sort of correlated noise, then life would be much more complicated. So basically the idea is that I have some truth, like a true polynomial, plus some noise. And in fact, that's exactly how I generated the data, if you remember, in the first place, right? And so this means that we should be able to determine the polynomial that kind of is what's called the maximum likelihood estimate, okay? So under this, under this hypothesis, or under this model, what we can do is find the maximum likelihood estimate of the weights given the observations. Right? That's like saying I want to maximize over the possible weights that I have the probability of seeing the observations given the underlying inputs and the weights that I'm trying to figure out. Right? So this is like saying, I want to find the W's that maximize this probability, okay? And again, if you took probability from me, I know we did this in class, right? So, how does this work? The idea is that, first of all, since we assume that all of the observations are independent, that means that I can decouple this into the product of n terms, right? This is like saying that I have the product, big pi, of n equals 1 to capital N of basically a bunch of normal distributions, right? That's like saying that what I expect to see in the observation is if my input data is x, I expect to see the actual value of x plus a bell curve around x that has a variance of sigma squared, right? So I have a normal distribution around each x. And I have what I see minus the model this is basically my mean, and then this is my 2 sigma squared, right? So this is basically saying that I have the input to the PDF is centered around the model, and then I look and see what that observation is, right? So it's like saying I have 0 mean noise given the model, right? And now we know from probability that if I wanted to maximize this, again, I have the same problem of taking the derivative of this and set it equal to 0, taking the gradient and set it equal to 0. So to maximize this, we would take the gradient of this and set it equal to 0. And what we would do is actually we would find out that we get the very same answer, right? So I'm going to save that derivation, I think, until next time, because I'm going to do it again in the PDF thing. So we can show that we get the same, basically, E of W, right? A different way of saying that is that the least squares model that we're fitting is also the maximum likelihood estimate, assuming that the errors in the variables are Gaussian distributed and have 0 mean, right? Which is a nice way of linking up why the least squares estimate is a good thing, right? It's like saying, well, we assume that our noise comes from some sort of natural probability distribution, and hence we can derive this is the right thing to do, right? And again, if you're looking for why is this true, we're going to do it in the next lecture, okay? So you can put a pin in that for a second. And then also just to say that, well, if we're doing probability, then you also know that I went on and on in probability about the Bayesian way of estimating things, right? So this is maximum likelihood. If you took probability with me, I would also say, well, what about the maximum a posteriori estimate, the MAP estimate, right? That's like saying, suppose I had some underlying hypotheses about what the parameters should be. That prior information should somehow enter into my probability. Well, the MAP estimate is basically like flipping these two things around. It's like saying, well, no, what I really want is to maximize the probability of, seeing the weights given the observations, right? It's kind of like the reverse. And you can show that the MAP estimate, the Bayesian estimate, is basically like, again, adding some regularization term to the cost function. That's where the lambda W squared comes from, right? That's like saying, if I already had some prior hypothesis, for example, that the weights should be small, then I add that to then I incorporate that into my probability model, right? So again, we'll talk about that a little bit more next time too. Okay, so I will say that the textbook that we're using, Bishop, is really all about, well, that guy loves Bayesian stuff, right? So if you have the textbook and you read forward in the textbook, you'll see that he's always trying to put a Bayesian framework on everything, right? While I will talk about it a little bit, we're not going to go like Bayesian hog wild for every problem that we solve here, right? One way of thinking about this is that we know we can always make a Bayesian version of every problem, but another way of thinking about it is that much of machine learning is maximum likelihood estimation. And part of that is that's very hard to have any sort of reasonable prior over the parameters, right? So say you've got some sort of like massive neural network, right? It's got billions of parameters. How could you possibly put some sort of reasonable prior values in those parameters? The best you could do is say, well, I don't want them to be too big, which is like regularizing it with this lambda. But it's not really like true Bayesian where you say, okay, I've got a Bayesian little prior for every one of these things. There could be coupling between the parameters. Like no one does that because no one really knows what a good prior should be, right? So that's why I'm not going to drill down into Bayesian stuff too much. Just to say that it does exist, and there is a whole thing I don't want to get into like today on what's called Bayesian versus frequentist machine learning, right? So like there's a whole world of Bayesian people who who will stamp their feet and say everything has to have a prior, everything has to be Bayesian. And there's some statisticians who will say, we have no idea what these priors should be. We should all just be doing maximum likelihood estimation and looking at the data and telling us, and letting the data tell us what the model is. So again, I don't have a big stake in this. I guess I'm nominally more Bayesian than statistical, but I'm not going to make a big deal out of it. Okay. Okay. So the last thing I want to say today is that, okay, so everything we did today so far was just like 1D data fitting, right? Fitting a curve to some points, and I could draw the picture in Matlab and look at it, right? But life in real-world machine learning is never like that. In the real world, you have maybe 10 input variables, and you have, you know, a number you want to predict, or you have multiple numbers you want to predict, right? So how does this get worse, right? So, you know, life is harder than this kind of 1D example. For sure, it's harder on the X side, right? I never just have like one number that I'm trying to use to predict some output. I have like 10 numbers or 100 numbers, right? So in the real world, I have many more than just X. Instead, for example, you know, we may have like 3 features, X, Y, Z, that we want to fit to some numbers F, right? So what would the polynomial problem look like there, right? Well, I mean, we would have a lot of terms, right? So we could have like, you know, constant term, X by itself, Y by itself, Z by itself. I could have X times Y, X times Z, Y times Z. I could have X times Y times Z. I could have X squared times Y times Z, right? If I think about enumerating the generic version of a polynomial, you can see it's going to get out of hand exponentially immediately, right? So, you know, even kind of a small mth order polynomial with, say, you know, d dimensional features, you know, has basically d to the m coefficients or weights. Right? So if I wanted to fit like a cubic polynomial to like 5 features of data, I'm going to have 125 numbers that I have to tune, right? So you can see that immediately, first of all, it's a much bigger problem. Second of all, I need much more data to be able to solve that problem, right? So, you know, we need a lot more data. For one thing. And the other thing that makes it more complicated a little bit is that, again, this is going to be a little bit hand-wavy, but there's something called the curse of dimensionality, which is not a very well-defined thing, but I need to say it because this is a machine learning class. So it's called the curse of dimensionality. So in brief, what this means is that things are, you know, more complicated, weirder, less intuitive in high dimensions. So, you know, while most of our toy examples in class are going to be 1 dimension, 2 dimensions, 3 dimensions, when you've got like a 100-dimensional vector, it's very hard to kind of like draw intuition from a 1D Gaussian to a 100-dimensional Gaussian, right? So again, this is something to look into a little bit. Like the book has some information on the curse of dimensionality. For example, you know, you may think of the bell curve in 1D as Gaussian and say, oh, well, you know, Gaussian basically means that everything is kind of concentrated in the middle. Most of the data is in the middle. Well, it turns out that a 100-dimensional Gaussian, most of the data is actually like kind of in a shell that's closer to the outside than the inside, which seems counterintuitive. The problem is that it's very hard to draw a picture on a piece of paper and reason about what's going on in high dimensions, right? And so that's just kind of like a warning, without being very specific, that, you know, you can't always just kind of like sketch something in 1 dimensions and assume that everything just carries over to 1,000,000 dimensions, right? That's not the way it works. We'll talk about that a little bit more as we get into this. So one thing on the homework, so now you should be able to solve the first problem on the homework, which is very much like exactly what I did here. And the last part of problem 1 is for you to fit some data to 3 variables, right? So, you know, it's much harder to understand like what the right answer should be because you're not going to be able to visualize what the right answer is. You just have to know that you did it right. In theory, it's the very same kind of matrix setup, but in practice, you know, you're not exactly going to know did I get it right or not, other than by convincing yourself. As with everything, I suggest that you know, debug your code with simple examples first, because your code should be just general, right? You should be able to write a general like curve fitting in any dimensions with any value of m, but it's easiest to debug it when you've just got a few variables and a few pieces of data, right? So don't just like solve the homework and move on, but think about like, am I doing this in a generalizable way? In a way, that's what homework is meant to do, right? Is I give you this training data, which is the homework problem, and you're supposed to generalize to be able to solve anything, right? It's a microcosm. Okay, any questions or comments about anything? All right, so like I said, generally for questions about like, why is this Submiti thing not working the way I want, or what should I even do on Submiti, please refer those to the TAs on Monday and Wednesday, or post questions on Piazza, and then I'll be around on Tuesday for other stuff, and I'll see you on Thursday. Have a good one.